Hello everybody, my name is Dmitry Panov, and this is a short video which introduces you to the course Representation Theory of Finite Groups, which I will teach you. So everyone knows what is a finite group, and I just need to tell you what is a representation of the finite group so that you know what this course is about. Let me explain to you. So let G be a finite group, then a finite dimensional representation of G is a homomorphism. So usually this will be denoted by row homomorphisms. So homomorphism from row from G to the general linear group of some dimension GL, for example, NC. So this thing here, GLNC is a general linear group. So these are basically invertible matrices. Matrices of size n by n. Yeah, just n by n. So maybe some of you forgot what is the meaning of homomorphism. So homomorphism is the following thing, is that, so it's a map. First of all, you see it's a map from G from one group to a different group, and it should satisfy the following property, that rho of A times B is equal to rho of A times rho of B. So here A and B are two elements of G, and rho of A is the image of A, and this is a matrix inside of GLNC, and rho of B is also a matrix. So product of two elements goes to the product of two matrices. So we will study, in this course we will study this type of objects, finite dimensional representations. Now I just want to give you one example, so where from such things can come, such representations. So this is something about symmetries. So everyone remembers what is a square. So here is a square with vertices 1, 1, minus 1, 1, 1, minus 1, and minus 1, minus 1. This is the square inside of the plane. Okay. Now you can ask a question, like, which maybe many of you know the answer. What are symmetries? Of the square of this square. I will just draw it like this, of the square. Yeah. So by symmetry we mean some kind of motion of the square which maps the square to itself. Then of course it's not hard to see that, for example, we have the following symmetries. We can rotate the square by 90 degrees. Yeah, so each point is just rotated by 90 degrees. For example, this point goes here, this point goes somewhere here, and this point is fixed. Yep. So we have can rotate by 90 degrees, by 180, by 270. So altogether we have say 4 rotations. Rotations. Yeah, I will just say here by 90 degrees, 180, 270 degrees, and we also can consider rotation by just identical map, which can be said rotation by 0 degrees. Okay, we have 4 rotations, and apart from this, we also have some other symmetries. Namely, we can take some axis of symmetry of the square, like for example this diagonal, yeah, and then we can reflect the square with respect to this diagonal. So it will look like this: point here will go here, point here will go here, and we have like some other axis of symmetries. So here we will get maps like this. Okay, so additionally to this we have 4 reflections. So like here was our question: what are the symmetries? And we see that we have 4 different symmetries, and altogether they form a group of 8 elements. This is clear. You see, of course, symmetries form a group. If you take one symmetry, then other symmetry, then the product is also composition is also a symmetry. So you see, like we see here the first part of the sentence. We see a finite group of 8 elements. Now, where is the representation here in this picture? So this is not hard to guess. For example, you see rotation by 90 degrees. So namely this rotation like this. Well, you know how to write it as a matrix. So is given by matrix like this. What should we see? So this point will go here, and this point goes here. In other words, well, the matrix is like this: 0, 1, minus 1, 0. Yeah. Now there was also this other element. This was a reflection with respect to this diagonal. So here again, it's not hard to see what's going on. So this basis element goes here, and this basis element goes here. In other words, this reflection corresponds to matrix 0, 1, 0, 1, 0. Okay. So in this way, to each of these 8 elements, we associate a matrix, which is thus acting on the 2-dimensional plane. So this is basically an example of a representation of this group of 8 elements. Well, kind of obvious representation, tautological representation, which comes basically from the definition of this group. And what we will do in this course, we will study different groups, different finite groups, and try to look for all possible representations which can occur. So you see, this is kind of related to symmetries of spaces. But this will be the content of this course. So that's it, and hope to see you all soon in the next term. Bye.